This assessment asks us to use the Claisen-Schmidt reaction to make the molecule shown on screen. I've gone ahead and redrawn it so that we can point to it as we think about how we're going to do this. The first thing we notice about this molecule is it's a little bit fancier than some of the other molecules we've seen. It has a trifluoromethyl group, it's got some stereochemistry, lots of things that distract us. But we're told to do this using the Claisen-Schmidt or the crossed aldol reaction between a ketone and an aldehyde. And so one of the things that can be challenging and that we need to do in this problem is ignore all the other fancy stuff and focus only on what matters. And that's what's happening up here. If we look at this part of the molecule here, we recognize that we have an alpha-beta unsaturated ketone. And we know that that alpha-beta unsaturated ketone is the product of the Claisen-Schmidt reaction, where an aldehyde reacts with the enolate of a ketone. Here's our ketone. This is the alpha carbon, so we're probably making this bond here. Right? This is the alpha to our ketone. That's where we're going to make our enolate, and this is probably where we're going to have the aldehyde. And so what we can do is we can put in some carbon numbers if we want. We don't have to number too many of them. Let's just call 1, 2. We'll just number the 6-membered ring, and then we'll call this one 7, and we can probably stop there with 8. What we know we're going to be making is the carbon 1, carbon 7 bond. Okay, so working backwards, let's just draw both molecules that we know we're going to be making. So here's carbon 7 and carbon 8. We have that. We'll figure out what needs to be there, although we have an idea that it should be an aldehyde. And then we'll draw the other molecule over here, the ketone. All the rest of the stuff just comes along as that sort of fancy decoration. It reminds us that when we do complex molecule synthesis, there are going to be other functional groups, but many times they're just going to hang around watching the reaction. But here's carbon 1, 2, 3, 4, 5, and 6. And so we said in our retrosynthesis, we believe that we're going to make an enolate at carbon 1. That can be made into an enolate, which would be a good nucleophile. And it's going to react with carbon 7, an aldehyde at carbon 7. So we can go ahead and draw in that aldehyde. And so we're going to react these two reagents. What base are we going to use? Well, in the traditional crossed aldol, that Claisen-Schmidt, we're going to use sodium hydroxide as our base. Sodium hydroxide is made using water as solvent, so we add sodium to water. And because we end up with the C1C7 pi bond, we know that we're going to be driving this reaction to eliminate water at the end, and so we're going to heat this reaction. So working backwards and kind of ignoring all the fancy stuff allows us to come up with this synthesis, which should make the molecule on screen. Before I go, I noticed as I was getting ready to erase the board that I left off the methyl group at carbon 3. Let's be careful not to do that. There's a methyl there. This should have been the product. So we actually have the methyl group there. This plus this in the presence of this gives us this. Sorry about having to add the extra 15 seconds.